related to ARCS, or what it has meant to you to be an ARCS fellow. And what's the other things, Amy?
I think that's it.
Let's say, so
That's good.
any personal stories that let us know more about you and your research?
Yeah, okay. Hopefully I can cover all of that.
Very casual, very casual.
Okay. Well, my name's Sarah. I don't know if you guys knew that already, but I'm
Almdari.
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 Yeah. Yeah, so I'm a chemical engineering PhD student, and I guess I didn't know I was going to do a PhD, right? Wow, I'm kind of nervous. It's a nice table. But as an undergrad, I'm a first-generation college student, so obviously, like, going to college was like this really big deal when I had first joined, and I don't think I really knew what I was getting myself into. I did chemical engineering, you know, not knowing what it was even, or what kind of job a chemical engineer worked. Like, I literally Googled the highest paying degree you can get out of a bachelor's, and I was like, that's the one I'm doing, which I thought was like this amazing thing, and it was really hard. Like, it kind of kicked my butt. So yeah, so apparently, you know, there's a reason they get paid a lot of money. So I had a really rough first semester in school. Like, I had a pretty horrible GPA. It was like 2 point something, and I was like thinking of dropping out, whatever. But what was really cool is it forced me to like kind of explore other opportunities. So I started getting super involved with like a group on campus that did a bunch of outreach, which was super exciting. And then it eventually kind of helped me find my place, which was in research. So I got involved with a professor at Arizona State. His name is Safat Ntange. And he kind of mentored me through doing research at ASU. So I kind of started this independent project, which was really cool, where I was running experiments on these cool 2D materials, which is basically what makes your phone be this like super fast, slim, beautiful piece of technology, right?
You're still an undergrad.
Yeah.
Okay.
So this is me in undergrad, and he basically kind of told me about how to get a PhD. He was like, this is this incredible thing you should do, like you're always in lab. And so basically in that search I started looking for programs at UW, and like obviously everywhere in the US. And so I ended up getting accepted to a few programs, and this is kind of where ARCS ties in, right? So when I got accepted, they offered us like a graduate incentive. I'm pretty sure ARCS does that through Dean Eaton, or did do that during my time here. And so just on my visit weekend here, you know, there was this like sense of community and like inclusiveness and diversity that was super important to me. And it was just cool, you know, coming here and like feeling so accepted, whereas I think at other institutions it just, you know, didn't feel like this right fit, right? Like, I knew I needed a community of support to be successful in my PhD, because that's definitely what I needed through my undergrad to be successful. And so yeah, I ended up at UW, and so I actually work with Jim Fentner, who is awesome. He is a total advocate for, you know, minorities in STEM and promoting diversity, and I love that. The only problem was he did computational research, so I had to like fully shift my perspective and kind of go from being this experimentalist who thought, you know, this is what I want to research, to, you know, kind of shifting towards more biosystems and kind of stuff that I wasn't super familiar with. But I knew I wanted to work for this person, and I knew that this work was important, and so that was really cool for me. Sorry, I lost my train of thought. So, yeah, so now I'm here at UW. I'm doing research in a computational lab, and so that's kind of this foreign concept to a lot of people, but basically what we do is we try and use a computational model to help experimentalists understand what's going on, or kind of elucidate things that they're seeing that they maybe don't understand. And for me, that's really fun, right? Because you get to picture every single atom on your screen, right? You get these beautiful images of like proteins that an experimentalist doesn't see. You know, they run tests, they get results, and they're like, what is happening? And so my favorite thing is when they bring us those problems, and they're like, can you help us, you know, kind of understand what's happening at a molecular level? And so we get to basically build these like ball and stick models that you probably remember from like general chemistry. And because we have these like super powerful computers here, we get to just simulate them and really understand what's happening in these systems, which is super exciting to me. And so what goes in hand with that is like the opportunity to study like things that I never thought I would have studied. So, you know, I study all sorts of systems, from like maybe just a water box all the way to these like giant proteins that, you know, might be important for, I don't know, a variety of applications, right? So I've worked on proteins that are relevant with your saliva, so it's called like a salivary protein, all the way to working with proteins that are important for catalysis, so in the biofuel industry. And so these are two very different applications, but it's been a cool opportunity to kind of just become an expert in all these like little bits and pieces of that. Yeah, and so in hand with that, I know you guys might have met Wesley Beckner last year.
Mm-hmm.
Yeah, he was a speaker. So in kind of tune with this, we're super active with this program called TechBridge Girls. And so what's been a really cool opportunity out of this, right, is we've been able to like kind of develop programs for these girls, which is awesome, you know, and like bringing the ability to code to like a young woman, like that is something I never experienced, and I thought that was like the coolest thing. So I mean, obviously having the financial freedom to kind of just do those things, like not every grad student gets to, you know, take off at noon every day and go drive down to SeaTac. But, you know, like we've been afforded those opportunities, which I think is super cool. Yeah, I feel like I'm rambling.
No, you're doing great.
Yeah, but yeah, that's kind of just been my experience in grad school so far and through ARCS.
So the various, if I can say it right, the computational models that you are developing,
Yeah.
where do you get, who's saying develop this for us? Is it coming from all sorts of different departments?
Yeah, so we have a ton of collaborators. We have some within the Chemie program at UW. We actually have a collaborator in Denmark that used to be a professor here but moved, who we love working with. They have these like fun little toy protein systems that are really fun to simulate. And yeah, collaborations with my peers too. That's the most fun, right? It's like when you maybe learn something from a project and you have kind of an idea that you want to like carry out, and just having the ability to like work with people around you has been really cool.
So when you create these models, and they're different than those that are just doing experiments, are they all going somewhere, or is it kind of a scatter, you know, like thinking of paint splatting and doing all sorts of different things?
Yeah.
Is under Professor, it was with a T.
Fedner. It's
Fedner.
spelled really
Fedner.
funky. It's P-F-A-E-N-D-T-N-E-R. A-E-N-D-T-N-E-R. I think I got
Wow.
that right.
That's a lot of extra letters.
I know.
So he was a real draw, but is it, I don't exactly know where these models are taking anything.
Yeah, okay, I understand. So basically, like any component, right, is made up of so many atoms, like right on the periodic table.
Sure.
Okay, so say we wanted to model a peptide, which is created from a bunch of different amino acid sequences. We can model every single amino acid using a ball and stick model. So say we want to model something like water, right? So water, the chemical structure of water is H2O, right? So it's got H, O, and then an H. And so basically what we can do is build a system that has two spheres basically, that describe these systems, and then we can propagate it dynamically through time using Newton's equations of motion. So it's very simple, right? It's this force equals mass times acceleration constant, where every single atom basically wiggles around. And so basically our simulations are setting up a box that might describe an experimental system. So an experimentalist isn't necessarily interested in a box of water, but what they may be interested is how a protein unfolds and refolds.
So are you a support system to experimentalists, or are you leaders in, I still don't know where these cool models
Yeah.
dancing atoms are going. I don't know, am I being?
Well,
No.
maybe, so when you're
I don't-
talking to lay people
Yeah.
or a big audience,
Yeah.
how does what you do, can you express maybe why the research you're doing is important to a room of people who want to write a big check?
Yeah.
Okay.
No, that's a great point. I definitely struggle with explaining this sometimes, but I think the easiest way is that, you know, an experimentalist can't answer this question without a model, and we build the models, right? So I would say we're almost one of the better groups at kind of gaining this intuition about it. So if we're not the group that's developing these things, and, you know, that's a feat in and of itself, right? So I feel like we're super accomplished on being able to like kind of build these methods from the ground up. We're a methods group, and then applying it to an experimentalist just kind of brings it to the real world, right? It's like they see something and you see something in your simulation that supports each other, right? And that creates this like really strong like idea almost.
So do you get to take that description of this one, and so if there was one project that you guys have built all these models, the experimentalists, and do you get to follow that into its application into whatever, human life, environment, whatever?
Yeah, I suppose we could.
But do you?
No.
No, you just create the models,
Yeah.
okay? But you would have examples of where the models are being used.
Yeah. Yeah, I guess one of the big goals is this idea of like high throughput computing, right? So I guess a common problem experimentally, let me think of a good example. Okay, so there's like this huge interest in renewable biofuels, right?
Okay.
So corn is kind of a common way of creating ethanol, right?
Right.
What a lot of people don't know is that you can actually use the feedstock, so the non-cellulosic component of corn, so the stuff that gets thrown away anyways, and convert it into fuel as well. But that process is extremely complicated. So what's cool is an experimentalist has found out that you can use a special substance called an ionic liquid to break down these components really well. The trick there, though, is that there's almost like infinite combinations of these different ionic liquids that you can create, right? So instead of having experimentalists maybe sit there and run a million different experiments, what's really cool is we have the power to almost like quickly shuffle through a bunch of these iterations and give them a better idea. So provide them a subset of like something to actually work with that's feasible, right?
Mm-hmm.
Does that kind of make a little bit
Yeah.
more sense? So I think
Yeah.
that's kind of the idea. I'm focused a little bit on the ground up level, but like that would be the ultimate goal, right? Is this idea of being able to like kind of give an experimentalist something to work with that's feasible versus, you know, having n to the power of n degrees of freedom.
And your department is called?
Chemical engineering.
What would your PhD thesis be about?
That's a good question.
Where are you in that process then? You're pretty early here.
I'm a little
You're
early.
going to be done with your third year ARCS fellowship
Yeah.
the end of this spring.
Yeah.
Yeah.
Yep. Yeah, so vaguely, I don't know. That's a good question. Maybe like any kind of, let me think about this.
You don't know yet. You
Yeah,
have to
I don't, yeah.
That's okay. No, I get it. You're you're not
Yeah.
at that stage yet. Yeah.
Yeah,
Yeah, that's fine. I get it.
cool.
Yeah.
How did your family react to what you're doing? And I mean your original family. I don't know if you have another family.
Yeah, my parents, I don't know if they know what I'm doing. I feel like they always ask how grad school's going. I don't know if they have this like grand idea. They're always just kind of wondering, are you going to graduate and get a real job? Which I think is funny because I feel like grad school is like my job right now,
Sure it is.
right?
Yeah.
Yep.
Yeah.
Absolutely.
And
But you said you were first gen,
yeah,
which is
Yeah.
very admirable.
thank you.